Hi folks, we've already learned how to name and write formulas for ionic compounds, and now it's time for us to do the same thing for molecular compounds. So that's what this video is about. We need some vocabulary first. A molecular compound is a compound whose simplest units are molecules. Okay, so what's a molecule? A molecule, remember, is a neutral group of atoms, so it doesn't have a charge, that are held together by covalent bonds. Held together by covalent bonds. So what's a covalent bond? A covalent bond is a bond in which electron pairs are shared between atoms. Usually these atoms are nonmetals. Metalloids sometimes get involved as well. But these are shared electrons as opposed to the transfer of electrons that we saw with ionic compounds. Remember that according to the octet rule, most atoms form bonds in order to obtain 8 valence electrons. Atoms are bonding to have a full valence shell. Just like we use Lewis dot structures to show ionic bonding, we can use Lewis dot structures to show covalent bonding. So here's an example. Here we have a chlorine atom. Here we have a chlorine atom, and if they come together, then we end up with a shared pair of electrons between the two chlorine atoms, so that each chlorine atom has 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8 electrons around it. So we end up double counting those central electrons because they are shared between atoms. But this is an example of a covalent bond and how the Lewis dot structure shows us how we can represent shared electrons. Now, in this case, I have 2 chlorine atoms, and so chlorine has the same electronegativity as chlorine because it's the same atom. And so this is an example of a nonpolar covalent molecule. Because they have the same electronegativity, they fight for electrons equally, and there are no partial charges on this molecule. Polar covalent molecules are shown the same way in terms of sharing electrons. We have hydrogen with 1 valence electron, hydrogen with 1 valence electron, and oxygen with 6 valence electrons. And when they join together, then we have hydrogen with 1 pair of shared electrons between it and the oxygen, and hydrogen with its own pair of shared electrons between it and the oxygen. So we represent polar covalent molecules in the same way. It's just that once we have a polar molecule, then we start talking about the directionality, where the electrons spend their most time. And in this example, electrons spend most of their time around oxygen because oxygen is more electronegative than hydrogen. So there is kind of a pull of electrons in the direction towards the top right corner of your page. Or of this particular picture, where the electrons are spending more of their time by the oxygen and less of their time by the hydrogens. We will learn more on how to draw these Lewis dot structures in the next topic, but right now we're focused on naming and writing formulas. So when we name molecular compounds, we use the prefix system. We use the prefix system so long as we're talking about binary compounds. And remember, binary means 2, so we're talking about compounds that contain 2 elements. Compounds that contain 2 elements that are covalently bonded together. So this is going to tend to happen between 2 nonmetals. 2 nonmetals. When we name these, we name the less electronegative element first. And remember, electronegativity decreases as we move left and down. Fluorine is the most electronegative. Fluorine is the most electronegative, and the further we move away from fluorine, the less electronegative the atom is. We're then going to use prefixes to indicate the number of atoms of each type that we have. There is a prefix to represent just 1 atom that prefix is mono, and we do not use that prefix on the first element. We never use that prefix on the first element, but we do use it on the second element if it's relevant to the compound. Just like ionic compounds, we are going to change the ending of the second element to IDE. So we are going to take the names of the elements off the periodic table and change the ending of the element name to IDE if it's the second element in the compound. Okay, I told you we were going to use prefixes, so here's a list of those prefixes, and you do need to memorize these. So mono means 1, di means 2, tri, just like a tricycle, means 3, tetra means 4, penta means 5, hexa means 6, hepta for 7, octa for 8, nona for 9, and deca for 10. So let's practice naming. CCl4, the first element is carbon, the second element is chlorine. So when we name it carbon tetrachloride. Notice that we did not use mono as a prefix for carbon because we don't use mono on the first element. Notice we did use the prefix tetra on the chlorine because there were 4 chlorines. And we changed the ending of the second element to IDE. Here's a compound between nitrogen and oxygen. We have 2 nitrogens and just 1 oxygen. And this is called dinitrogen monoxide. There are 2 nitrogens, so we use the prefix di. Now, with this oxygen, this time we do use the prefix for just 1 atom. We say monoxide because there's just 1 of them. It's only when the mono would be on the first element that we don't use it. Again, we change the ending of the element name to IDE. SF6. This is sulfur hexafluoride. Again, we do not use the mono prefix. Even though there's just 1 sulfur, we don't use the mono prefix because it's the first element listed. And then hexafluoride. Hexa means 6, and we change the ending of fluorine to fluoride. So, naming covalent compounds is easier in many ways than naming ionic compounds. The trick is that you need to recognize that it's a covalent compound so that you know which rule to use to name it. So here, carbon is a nonmetal, chlorine is a nonmetal. Nonmetal and nonmetal means you've got a covalent bond. Similarly with nitrogen and oxygen, these are both nonmetals. Similarly with sulfur and fluorine, these are both nonmetals. Okay, how do we go about writing the formulas? The formulas follow from the names and the prefixes given. So arsenic trichloride tells me that there's going to be 1 arsenic because there's no prefix, and there's going to be 3 chlorines. So 1 arsenic, 3 chlorines. For dinitrogen pentoxide, I can see that there will be 2 nitrogens and 5 oxygens. So my formula is N2O5. For tetraphosphorus decoxide, tetra means 4, deca means 10. So I'm going to have 4 phosphoruses and 10 oxygens. Tetraphosphorus decoxide. Again, these are fairly straightforward. We just need to recognize that we are dealing with a covalent compound and therefore follow the covalent rules. But this is very easy when you're given the name and you're going to the formula because of these prefixes. Ionic compounds never have these prefixes. So if you spot a prefix, you know it's a molecular compound. You know it's covalent. And you need to follow the covalent rules. So there are 7 important molecules that you need to know about because they don't have fancy names. We just name them after their elements, but they are molecules, not individual atoms. And these are the 7 diatomic elements. So these 7 elements are never found as single atoms in nature. They always pair to form small molecules unless they're bonded to something else. If they're bonded to something else, you can find a single hydrogen or 3 hydrogens or 4 hydrogens in a compound. But if they're not bonded to anything else, then they bond to each other. So hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine are the 7 elements you must memorize, that they don't come as singleton atoms, they come in pairs if it's the element on its own. Notice this pattern on the periodic table. This formation of diatomic elements over here actually looks like the number 7, and then you just need to remember to add in the hydrogen as well. So these are the 7 diatomic elements. I hope this helped.